Okay, so we have this circuit here on the left hand side, and I want us to find what VO is, which is going from the bottom to the top, as you can see in the diagram, right? So the Nava gave us a technique to use. I know I could use Nodal or loop, but as I said before, I picked the one that had the least in. So I have, well, I could pick to have I1, I2, those are loops. And your nodes, when you label any nodes, the first thing you have to do is get a reference, which is your ground. So the Nava gave us a reference here. Your ground could be anywhere. The killer should be anywhere. Don't always have to be on the bottom. Just natural to put it at the bottom. So you can see the rise and everything. So I'll put it at the bottom here, which shows you are custom. So you have that node here. So now you can draw any node. So you have this node here. You have this node here. It's this node. Remember, nodes are bounded by the components, right? This node took in here, and you have this node at the bottom here. Alright, so the third thing you do is you label the voltage of the nodes that you know the voltage for. So there's ground, so there's zero for sure. All is zero between the bars. Because this is zero and there's a battery, 0 plus 186, this have to be 186. It just have to be, because you know 0 plus the battery is 186. If you didn't know what the voltage before the battery was, you cannot just assume this to be 186. So be careful, right? The only way this could be 186 if the negative side of the battery or the opposite side of the battery is at a reference at 0. If the polarity of this was reversed, so like if the plus was here and the minus was here, this will be 0 still, but this will be negative 186. Yeah, and the only time we could assume that is if you know the opposite side of the battery is at the reference, which is 0. So let's be careful. Right, so other nodes I know the voltage for. This is our voltage dependent source, so it's our voltage, yeah, voltage dependent source. So this here is 0. So this side here is what I was talking about here. This would just be minus 1.6. Let's erase this. 1.6 I, whatever that is, you know where it is. I triangle, you know where it is. So it'll be negative 1.6. The reason why it's negative because it's on the negative side of the battery. And the other side is at a reference of 0. So 0 minus 1.6 I triangle is negative 1.6 I triangle. Yeah, that's all that is. So now you have all your nodes that you actually know the voltage for, and the nodes that you don't know the voltage for will be here, so you can label this VA, and down here, which is VB. So luckily for, remember, this is our loop here. So we have two unknown nodes, and we have two loops. So in this case, it wouldn't really matter which one we pick, they're kind of equal. Yeah, but as I said before, you could use any analysis technique you like. Me, I love Nodal, so I could use that for everything. Sometimes it could be very inefficient. So you have to know both. Because you could be there calculating the whole day, and your calculator could only go so much amount of equations to solve at the same time. So anyway, I will use Nodal. So I run through the Nodal, same steps I showed you last week. It ain't gonna change. So after you label your reference, you draw in your nodes, you draw the voltage of nodes that you know the voltage for, you analyze your circuit. The next thing I have to do, I say I use a nodal. So I have to open my big eye and look to see if I have any supernodes. What a supernode is when you have a voltage source in between two unknown nodes. So I repeat, a supernode is when you have a voltage source in between, actually sticking or joining together, two unknown nodes. So it have to be two unknown nodes at the same on both sides. So you have this voltage source here, which is the 43 volt. VB, I don't know the voltage for it. VA, I don't know the voltage for it. So this here will be a super node. So how you treat with it, you combine the two to make one complete node and you treat it as one node. So all this here now, power, remember it bounded by the endpoints. So now all that is now one node, or you call it a supernode. Yeah? So now we have one node, we don't really have any other unknown nodes. So now we could start our analysis. So after you do all that, you analyze your supernode. If anybody asking why these two aren't supernodes, it's because you know the voltages on both sides. So there's nothing to find out there. Yeah, so nothing, no information there. So this one here, you don't know what VA and VB is. Trying to get a bar voltage source. So you make a supernode. You join the two nodes together, which is just joining the endpoints together. You have a supernode. So when you're starting the analysis technique, the first thing you have to assume is the direction of the current, either going into the node or out of the node. It don't matter which one you choose. So I just going to assume the currents, in this case, to go outwards. So you state assuming current leaving node. Okay, you must state this. So we start. We only have one node that we need to do the equation for, which is this one here. I like to draw dots at the endpoints. So I have 1, 2, 3 endpoints. So I know I have three little things. So remember the little thing I show you. So if the current going out, the same equation, so where you're coming from, so the node you're coming from minus the node you're going to, divided by the resistor in between them. Same gibberish. So I coming, so if I start in here, so it'll be the node I'm coming from minus what I'm going to, divided by the resistor in between it. So it is 186, not 0. Yeah, 186. So we're coming from minus we're going to, divided by the resistor in between it. Plus, down here now, so we're coming from minus we're going to, which will be minus 1.6. So it will be a plus, divided by the resistor in between it. And plus we're coming from, which is on this side here. So you're coming from VB minus we're going to, which is 0. Okay, we're going to 0. Divided by the resistor in between it. And that is your 3 endpoints. And it does make it equal to 0 at the end. So that is your first equation. So I like to make it into one nice equation one time, but for now we'll leave it like that. So the second thing we need to do is write our super node equation, which as I said, you just start from an endpoint in the node, you add up all the voltages in the correct polarities, and you just equal to the sum of the last node. So in this case, if I start at VA, it will be VA minus star plus, so it will be plus 43. And it will equal to the sum of the last node. Once you reach the last node, just write equal to whatever it is. So there's your supernode equation. Yeah, and third thing is, after you analyze, that is the only unknown nodes that we need. Remember, the supernode combine the two unknown nodes first, and it have no other unknown nodes, so I don't have to do anything else. So the last thing you have to do is write the equation for the dependent source. So you only have one dependent source, so which is I triangle. So there's the exact same thing I showed you all just now, right? So I triangle, look where I triangle is on this side here. So I triangle up here. So let's look at the circuit and analyze it a little bit, right? So I triangle going through this branch here. So that is the current flowing through the 2 ohm resistor. So let's follow the current because we need a resistor. We need one. We need one. Remember the what I show you on top here? You need a resistor. There's this here. And the next thing you need to know is the voltages on the both ends. Yeah, it's the same concept. So what we have? VB and 0. We know what 0 is. 0 is 0. But we don't know what VB is. But we know an equation that could give us VB. So tell me if I'm wrong. If I add VA and I add 43, won't I just get what VB is? Remember, the voltages cumulatively add up together. The same concept. That is why this is your supernode equation, right? So VA plus 43 is equal to VB. Yeah? And remember, current is voltage divided by resistance. So I have a resistor, the current going in this direction. Yeah? And a normal arrow will go from a high potential to a low potential. Yeah? So be wherever, remember where we're coming from, minus the node after. Everything here is in normal operating conditions. I mean, you can clearly see that because the set is 0. So now we know it will be, so we're coming from, which is VA plus 43. That is what VB is, right? VA plus 43. Minus 0, I mean, kind of redundant, right? And 0 at that point, and it divided by the resistor in between it. Yeah, I forgot to write that in the top piece. Well, I mean, there's if you're looking for voltage. So if your current is divided by the resistor here. Yeah, so kind of reasonable. So that's why your dependence was I triangle or whatever is. I triangle is the current in this branch, which would just be the current flowing through here. The current going in that direction, you have a voltage drop with the arrow, but in the same direction, so it's normal operating conditions. So the little trick is, you know that you're coming from, subtract the node after, will give you, well, in this case, the one current, so you divide it by the resistance, and you get your answer. So that's that. So we have 3 unknowns, 3 equations, so we inside. So the next thing we have to do now is not really solve them, yeah, you're trying to solve them simultaneously. So you play an equation into the next equation and reduce. So we could label this one 1, 2, and 3. So we have I triangle here, this I triangle. So you can make that substitution and then we will continue from there. So let me go through. So I did the question already, so I'll just write down what I have. So from the top piece, you'll have VB minus 186 on 22 plus VB, and you have plus the 1.6 divided by the VB, sorry, multiplied by the VB plus 43 all on 2. And all that being divided by 14, and you plus the VB plus 43 on 2. So this piece here is what VA is. So if we go back on top, so V, kind of write in the reverse order, so small thing. So VB is VA plus 43, so this would be VA here, not VB. Right, VA. That is what it is. So from on top here, VB is VA plus 43. So you just gonna put this here. So you just end up with VA plus 43 on 2. And this here is I triangle. So you can put him here. That is what I did. So you can put this equation here, make it equal to 0. And from here is where arithmetic skills will come in, everybody at a different level. So what I will do is expand out this piece here first. So 1.6. So I get VB is the last line on the right. On 22, and you have plus VB plus, and 1.6 by VB on 2 is 0.8 VB, and then 1.6 by 43 on 3 will give you 34.4. Alright, now all being divided by 14, and you plus a VA plus 43 on 2, and you make it equal to 0. So now we could simplify this piece here. So VB minus 186 on 22, 1 VB plus 0.8 VB is 1.8 VB plus 34.4 all over 14 plus VA plus 43 on 2 equal to 0. So at this point here now we're trying to get rid of the fractions. So you multiply everything by a common denominator. So to get the common denominator, you could just multiply everything here, and that will give you something that will be a common denominator for everything. So in this case, 22 by 14 by 2 is 616. So you multiply everything throughout by 616. So all the denominators will disappear. So when you multiply it out, you end up with 28 VB minus 5208. Then you have plus 79.2 VB. Oh no. Right. Plus 79.2 VB plus 1513.6. And you have a VA, which is an issue, but I'll sort out that just now. Plus 13244 and is equal to 0. So we are at a junction, but I just made a small, this will be VA, not I'll keep what I have, so I'm not just run through that to show you something, which is very important, which is I'm glad I made this mistake, right? Well, it's not a mistake, that's how I label it and how I do the working. So on this side here on the right, I labeled wherever VA, I put it as VB. So this on my working is VB and down here is VA. You'll get the same answer. It don't matter how you label your notes. You'll get the same answer. Alright, so when I was doing it now, all I would change to get into how I have it is that this A will swap to B, this here will swap to B, and that's we swap this VB here will swap to the VA that I originally had. Yeah, that's swapping the notes. So down here now we'll just swap. Because now it will be VB plus 42 will equal to the VA at the end. Same idea. Nothing changed. I just inverted the nodes to why I have it. I don't wanna do over the simultaneous too much. And then down here now, here will be VB plus 43. Alright, so now go through my steps and I could just have my VB here, like how I custom, how I do my working. So everything is well with the earth. Right, so I'll run it back through again so it won't confuse you. So be here, and then down here, everything good. So the reason why I had to do that, so when I did the question, on this side I had VB and VA. When I showed you just now, I had VA where VB was. You will get the same answer. You'll get the same answer. Nothing gonna change. But when I reach down to this line here, which is this here, I will end up with a VA. So I had to change all my VBs to VA, which is real work to do. Right? Because I already did it on my paper. So what I just did, I just inverted back to what I have. So all the VBs would just swap to VAs in this case, and everything else would just fall back in line. Alright, so it wouldn't change the answer, it wouldn't change the price of cheese. Alright, so you'll get the same answer no matter what direction you choose or how you label your notes. So it will be the same answer regardless. So down here now you add up your VBs. So you get 415.2 VB plus 9549 plus 0.6 is equal to 0. And well, at that point, kind of elementary. So again, negative 23 volts. Alright, and if you want what VA was, you have an equation that can give you VA. VA is VB plus 43. So VA would equal to negative 23 plus 43, which is 40, well, what is it for VB? So 23 plus 43, 20, no problem. So 20. And that's so VB is up here. All right. So and VA down here, 20. So what will V0 be? So let me analyze this based on the same technique I showed you just. So if you were to erase this and look at the direction of the current going down here. Yeah? Your voltage, remember current does go from a high to a low, right? So in this case it's going here, which is in the same direction, right? So that means you had to go from something up here down to zero. Yeah? So because it's in the same direction. So you expect here to be technically higher than here. So whatever you get for VB, that will be the answer. So it'll be negative 23. And that is basically it. The reason why is because this down here is zero. Yeah? Yeah, nice. So that is it. That was BB. That is all it is. So you just nodal analysis. Same steps. You label in your reference. You label your nodes. Label the nodes you know the voltage for. Look for your supernodes. Loop them together. Do the equation for the supernode and any other unknown nodes that you don't know the voltage for. And after that, you do your little analysis techniques. The node you're coming from minus where you're going to divided by the resistor in between it. You do that for all. If you have a supernode, write your supernode equation, which is just the sum of the voltage in a particular direction inside the node, would that equal the last node. Then you analyze your dependent sources. Alright, and once you do all that, you solve it simultaneously and you get your answer. Alright? So this question actually on YouTube. So you can check it out and he explained it in the same general way. So it's the same idea as we were doing before. So any questions on that before I continue? That is the answer. Raw nodal analysis. Nothing has changed. Alright, okay, so nice. So that's what we have there. So we try next one. So this one is a past paper question. So same idea. So what he wanted to do in this question, he will tell you, alright, use nodal and loop and derive the system of equations. So that's what we're going to do here. So same analysis techniques, nothing has changed. So when we start with nodal, as a matter of fact, let me do loop. Find me kind of slacking up with the loop analysis. So I go through the same idea, same general steps. You don't need the voltages for loop. Like a reference voltage, you don't really need it because it's just loops you care about. So the first step, you join your loops. So there's I1, I2, I3. Yeah, so all the currents have to be in the same direction. So you can have some going clockwise and then some going anti-clockwise. So you have your loops. So the next thing you have to look for after you label the loops, you have to look for something called a super loop. So a super loop is the opposite of a super node. So a super loop does happen when you have a current source being shared between two loops. So if this here was a current source, dependent or independent, it will make I3 and I4 a super loop, but it's not. So therefore the circuit has no super loops. This is a current source, yes, but it is not shared in between two loops. Yeah, so it have no super loops. So because I like it, just continue like normal, like a normal question. So it really matter what loop you start on. So you can start with I1 because that's kind of logical. So with I1, first thing I assume is you assume the direction of your voltage drop. So we're gonna assume it to be like how we accustomed with it. So you just gonna assume the voltage drop across the resistor to be negative. We can assume it to be positive. Anyways, it's basically the equivalent of you saying the direction of the current either going outside or into the node. For loop analysis, you either assume your voltage drop to be positive or negative. It's not going to change much. So we're just going to assume it to be negative. So start with the I1 loop. So you go up, you come across. So this here will be, so you can say for I1 loop, so it can be minus 10 I1. So you're here now, and now you're going through this resistor. But the catch in this resistor is that you have two currents going through this resistor. So you don't have to be afraid. So it will still be minus 10 I1, but the current in the opposite direction will be the opposite sign. So it will be plus 10 I2. Yeah, because you assume a forward direction will be negative. So anything going in the opposite direction will be plus. And we're here now. And let me go into the 30. So same idea. So it will be minus 30 I1 and it'll be plus 30 I3. Okay, going in the opposite direction. And you're back to where you start. And that'll just equal to 0. Yeah, that was I1 loop. So the I2 loop, same idea. So it doesn't matter where you start. You probably start here. So you're going through here. So there is a voltage source, which is okay. V is equal to IR. So I by R is voltage. If they get the voltage source, you get through. Remember, loop analysis, you want the voltage drop across the components. So if some get the voltage drop, you get through. The reason why the super loop does exist is because you don't know what the voltage drop across our current sources. So that's a problem. So you will love current sources in Nodal and you will hate current sources in loop. Yeah, okay, it tends to be the opposite. So anyway, we started at B. So going through that, we have voltage rise. So it's 1, we're here, come down here, going to the 40, so it'll be minus 40 I2 and plus the current in the opposite direction, which is I5. And here now, when you go back to here, and then you have minus 10 I2, then you have plus 10 I1 in the opposite direction, and you're back to here, and you make it equal to 0. So 1 minus 40 I2 plus 40 I5, here now minus 10 I2 plus 10 I1 equal to 0. I3 loop, so where's that? That's here. So the issue with this one is I already have a current source that is synonymous to that loop alone specifically. Yeah, so anytime you have a current source that is the only current source in a loop and it's not part of a super loop, that will be used to derive the equation for that loop. Okay, remember, okay, if you look at it, this current source, you don't know what the voltage drop across it is, but it's not being shared by any other loops. So therefore, the current source here is the current in the loop. Yeah, so if this current source here was a current source, the equation for I2 would be this current source in the correct polarity, because in this current source not being shared by anything else. So down here you have a current source not being shared by the only current source in the loop. So if you use the correct polarity for this, I3 will be minus 1, because remember I3 going in the opposite direction. So it'll be minus, right? And that's that. And then I4, same shalala. So start down here, doesn't matter where you start. You go up, so that'll be 5ix, because our voltage source, E. So you're up here now, then you're going across, nothing, come down here. So we minus 20 I4 plus the current in the opposite direction. So you're here and you're back to where you start. That one was a short one. Then you have your I5, which is your last loop. So we start down here, so it'll be minus 20 I5 plus the currents in the opposite direction, I4. Up here now going across, so it'll be minus 40 I5 plus the current in the opposite direction, which is I2. Here now, then you're going through the 100 ohms, so it'll be minus 100 I5, and then you're back to where you start. And you just make the whole thing equal to 0. Alright, and the last thing you had to write is your dependent sources. So you have one dependent source, which is Ix, but in loop analysis now. So Ix would just be I1, because it's literally in the same direction. Yeah? And so there's your dependent source. So a current dependent source in a loop analysis is nice, because you already have loops. And if they give you like Ix, is either going to be opposed in the I1 or hidden or in the same direction. So whatever Ix is going to be the same current as I1. If Ix was in the opposite direction, it would be minus I1, because in the opposite direction. Alright, if you have a voltage and loop, that means you have to use IR. Yeah, that's the same way how you did it before. And that's that. So what you would do, what I didn't do here, is simplify the equation. So group all your I1s, your I2s, your I3s together. Just group them together, make them look nice, and that'll be it. Yeah, that's basically it. So I will do the nodal, but I want you all to try. So the nodal is the same steps, just different playing field. Label your nodes, there's ground. Label your nodes, you have a super node here. So you have to group this node here, group that node, make it into one big node, do your super node, whatever, and you derive your system of equations. Same thing. Not gonna change it. You just know how to solve it in this case. So just wait to get the equations for it. Alright, and some cool is you have a current going in this direction. Assuming we do a nodal. So you have a node here, and you have a node after. So like you say there's VA and there's VB. Current going in this direction. So if current going in this direction, the arrow will be going from a plus to a minus. Remember the current here going through here will be a voltage drop, because current is from a high potential to a low potential. Yeah, so this here will fall straight in line with what I did up here. This with this here. So the current through here, if you was doing nodal, it will be VA minus VB. So where you're coming from, I'm sure you came from VA minus where the node after. In this case, since you have current, it is divided by the resistor in between. So that will be Ix. As if you do nodal. If for loop, Ix is I2. And is. So you will have to do the same equation for all your unknown loops, so unknown nodes, dependent source, which is what I just did there. Look out for your super nodes, and it should be good. The only thing that could trick you up is your dependent sources. And I cannot just give you a cheat code for that. Yeah, for loop, if you have a current dependent source, you can't true. You already have loops running everywhere. Either gonna be minus or plus. If you have a voltage in loop analysis, you have to do the difference of the currents by the resistance, which here you should already have. Alright, that is basically it. Alright, so yeah, that was all. Any questions on that one? Alright, so I'm gonna show you all something. I just want to cover on the basis. So if you're asking about the currents, so let me set something. So let me say we're doing loop analysis. Alright, we're doing loop. And let me say they give you an arrow across here, and they say high potential, low potential, and the label of VO. So you're in loop analysis and you want to figure out what the voltage across here, or equation for it. Remember, in loop analysis. So you have I1 going here, and you have I3, blah, 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 blah. So what you do, draw your currents, or your directions for your current, my word, no, change the color. So you have I1 going here, and then you have I3 going so. So same concept. Which current here will have a voltage drop across this resistor here will be I1, and I3 will just end up being the opposite. Alright? So we know V is equal to IR. So in this case it will be the sum will happen with the I, and the R will still be 30. That's okay. So I write it in the correct polarities. So which one will have a voltage drop? So since you assume your currents or your drops across the resistors to be negative, yeah, remember you assume that in the initial part of the question. So this I1 here would be your normal drop, like what you did before, which is your minus I1 by 30. I'm gonna write it like that. So it'll be minus I1 by 30, or minus 30 I1, right? And then this I3 will have a voltage rise, as you can clearly see, going from a minus to a plus. So with respect to what you said in your assumption, this will have to be a plus 30 I1. Yeah, and then from here you could just factorize the I1 or factorize 30. So you could just end up with I1, and it's supposed to be I3 now. Where did I get that from? I3, because that is this one here. So you gotta be careful. Right. So you end up with plus I3 minus I1. Yeah, and that will be the equation for it. But the concept is with the same thing I explained here. So you have an arrow indicating voltage drops, voltage rise. I1 is the only one that you have a voltage drop across the resistor. So based on what you assume your voltage drops when you're doing loop to be negative, which is okay. Remember, you use that for everything else. So in this case, I1 could be your normal thing minus I1 30 or minus 30 I1, and anything going in the opposite direction will be positive. So that way you get the plus 30 I3 in that case. And the sum of those two will give you what your VO is. So that was that. So that's how you will do VO if you were doing loop analysis. Yes, I hope that helped. Okay, so let's run into what else we have to do. So Z19, so let's run through Thevenin and the steps. So I hope that was helpful. Remember, if you have any questions, you can always stop. Okay, so Thevenin. I don't know how to show you Thevenin, but it's the same things that you had to do. So what Thevenin is, if I had to short it in a concise manner, think you have a million and one resistors in a circuit, a million and one components, battery, current source. It's just looking confusing, right? And let me say you pluck out a resistor in that million and one circuit components, and you want to see if I was to increase the resistor at a particular point, or if I was to reduce the resistance of it at that particular point, how the current would change in the circuit and at that or through that resistor. So what you would do is you will reduce the entire circuit into an equivalent resistance, and you will find the voltage at the particular point where you have the resistor. So if you're looking at this diagram here, so this RL or your load, this is what we want to manipulate. We want to increase it, decrease it, and see how the voltage and the currents in the circuit would change due to me manipulating that. That is basically what Thevenin and Norton is, just a circuit reduction to make the analysis simpler. So if you have the entire circuit reduced to one resistor and a voltage source, you can manipulate your RL and you can know how the current will change depending on how you manipulate it, which is the beauty of Thevenin and Norton. Alright, it literally just with that you don't have to care about anything else in the circuit. Yeah, you just don't care about it. But what you care about is the value of your load resistor or where you manipulate it. Because once you get manipulated and you can just plug it back into the same circuit, which I will show you, and you will just get the current through it. So Thevenin, when you're doing Thevenin, this equivalent circuit for it is our voltage source, you call it V Thevenin. Then you have your equivalent resistance looking into the circuit from your load, and then you have your endpoints. So this here is where you will potentially plug in your load resistor if you had one to do the calculations with. So but you have the entire circuit reduced into a resistor and a voltage. Yeah? So this is basically we're trying to, so when they say reduce the circuit into its Thevenin equivalent, that's way to find the R Thevenin and the V Thevenin, or the Thevenin voltage. Alright guys, that basically what it is. And this part here is just where you're putting in your component that you want to manipulate. Alright, and Norton is the opposite. So in Norton, you have a current source, which is I Norton, or I capital N. But in this case, your R Thevenin, instead of it being in series, it's in parallel. So it's in parallel, and then you have your load points connected here. Yeah, so that's that. So let me go through these steps. So I'll start with Thevenin, right? And we'll run through this question here, decide, and call it a day. So the first step is for Thevenin, you remove the load resistor. So in this case, since the Thevenin through here, you will have to open circuit, so that's no longer here. Yes, but you have the endpoints. Yeah, which are these endpoints here. So you move the load resistor. So the second thing you have to do is you have to find the R Thevenin looking in from the endpoints. So you're basically trying to find the resistance looking in from here. So you basically kind of enter any circuit here and you're going out. But I'm going to use that. You enter any circuit here and you're going through the circuit. Right? But the steps to do this, so the first thing you have to do is you have to take off all your independent sources. Right? Independent. Note I say independent. For dependent sources, it have a totally different method you have to use. There's only for the circle, not the diamond. So you open your current sources, because the only way for you to stop a current is to break the circuit, right? And you short all voltage sources, because the only way for you to make a voltage disappear is to make it a short circuit. Yeah? So that's that. So if you were to do it on this side and redraw the circuit, so this part here will be a short circuit. You have a resistor. This is our open circuit. So you just end up with this. Then you have here the resistor there, which is the 5 ohm. Then you have your 9 ohm. And that is the end of that. Remember, there's your endpoints here. And you're looking in to find R Thevenin from Yeah. So you're kind of going in here and coming back here. This is the equivalent of you reducing the entire circuit into a equivalent resistance. So what you could do actually is take off the voltage in the circuit and get a multimeter, plug out a resistor, and you just plug in your terminals across those 2 points. So you plug out the resistor, you put in your terminal here with your multimeter, and it will give you the resistance, but it will give you the equivalent resistance looking in at that particular point. Yeah, because if you change the point that you're looking through from, the equivalent resistance would change. Because depending on how we look through it, remember some voltages and the current sources will some will give you a short circuit, some will give you an open circuit, depending on where you look through. So the impedance or the equivalent resistance will change. So you should just measure the resistance looking in at that particular point. Alright, so where are we now? Alright, so we have 9 here. So we're trying to get the total resistance. So we coming through here. So that's how let's do it. Here's our man walking. Cool. You're walking across. So you're going through that 9 ohm. Good. They're here now. So you have a choice. You can either go through the 5 and end up here, or you could go through the 4 and end up back. So therefore, is your 5 and the 4 in parallel with each other. Yeah, so this here will be 9 plus. When you have parallel, it's products over sum. So it will just end up being 9 plus calculator product 5 by 4 divided by sum. You get 2.2. So you add that to 9 and you get 11.22 ohms. So that is R7. So it's the same steps. You remove your load resistor, no matter what type of mad circuit to give you. The first thing you remove the load resistor. Then you find R Thevenin, you looking in from that point. To do that, you open circuit all the current sources, all the independent current sources are capacious enough, and you short circuit all the independent voltage sources. And then from there, you find the equivalent resistance looking in at that point. The easy way to do it is think of yourself as a little stick man and you're walking into the circuit. If you walk through a resistor, it's in series. If you reach a point and you have options, it's in parallel. Okay, you're trying to end up at the same point, which is here. So if you could go here, here, or you could go. So that had to be in parallel. So you end up with that. So that are Thevenin. So in the circuit from this side, so far, we don't know what V Thevenin is, but we just find what R Thevenin is. 11.22 ohms. So we are on our way. So the next thing I do is find V Thevenin. And we know two analysis techniques that we could use to get voltages and currents in our circuit. We have loop and we have nodal. Yeah, so I love nodal. I'm looking for voltage. So I will use you should use loop if you're looking for voltage and use nodal if you're looking for current. But I bias, so I can use nodal. They could use loop. But for me, I personally, if the end give my choice, I will use nodal. I just like it. But practice both. I just like it. 'Cause you have to do both for your exam anyway. So you have to appreciate both of them. But when given a choice, you will always favor one over the other one. It's just kind of natural. Somebody might like loop, but whatever method that you like, just make sure that you know it with all the possible things that can happen. Because every method has its drawbacks. So it's kind of hard to get voltage while alone with nodal, and it's kind of hard to get current alone with loop because it's kind of working with backwards. Because loop analysis is IR, which is voltage. Nodal is VNR, which is current. So you kind of give an indication as to which method will be easier to find one. But anyway, let's me rambling. So I'm gonna use nodal. So when I do any nodal now, I have to go back to my original circuit. because I can't use the one where I use for R Thevenin, because I will get the completely wrong answer. So I'll go back here. So basically at this point here, what you're trying to do, you're trying to get the voltage here. So basically it's equivalent to you plucking out the resistor, taking a multimeter, measure the two terminals and get the voltage across it. Because remember the idea what you're trying to do, you're trying to break apart the complicated circuit into one resistor, so that resistor will model the resistance of the rest of the circuit, which I don't care about, and I want a voltage which would be at the endpoints here, which would not change, constant. Once I close the circuit by putting in my RL, I know it will be 10 no matter what. So you just reduce the whole circuit, enter resistor and a voltage, and you could play around with your RL and see how the current would change through that particular resistor. Yeah? And you don't have to worry about the rest of the circuit. That's the beauty of it. So let's run through this. Nodal, same steps. It should be about that. First thing you do, reference. Go on. So this whole thing here is 0. Remember this still open circuit to that. That's the first step, line change. All this here is still open circuit, so that's that not here. Right now it does have two endpoints here. Alright, so that is that node there is 0. Cool. This have to be 50. Why? Because it's 0 plus 50. What else we have? We have this node here, which we don't know, so you name it VA. This here is not a node, so you just leave that just. It have no current flowing through the 9 ohm resistor right now, because it's an open circuit. It have no closed path, right? So whatever you get for VA will be the voltage here, because you could basically treat this 9 ohm as a short circuit right now. Okay, so now what we have to do is get the equation for VA and solve. I think I have enough space on top, so I'll do it here. So same chalala, yeah, assume a direction for your nodal analysis. So I'm going to assume it to be going outwards, whichever one you choose, it don't matter. So same thing, where you're coming from. So you have one endpoint here, two endpoints, 3, and here, yeah, button. You will see what it is here. So if I start in here, so we're coming from minus where I'm going, divided by the resistor in between it, plus down here is a current source. Yay! Current, I want current. They gave me the current already. So in the correct polarity, I assume the current going out. You're going in the opposite direction to what I assume. Why? I don't know. So we just had to end with the polarity. So that would be minus 3. So that there, we do there. Here now, where I'm coming from, minus where I'm going, which is to ground, and I'm going to put minus 0 divided by 5. They kind of redundant at that point, right? And this point here, V is VA minus 0. This here, it have no voltage here. And also this here is not 0. There's an open circuit. So you don't know what it is. So it have no current flowing through there. So it does 0 plus 0. So you can just make that equal to 0 at that point. Yeah, it have no current flowing through here. None. Because it's an open circuit at the end. No current flows through an open circuit. If you have no current, you have no voltage drop. Yeah, so at that point, we could reduce, multiply everything by 20, a common denominator. So you end up with 5 VA minus 250, and that'll be minus 60, and then plus 4 VA equal to 0. Simplify, 9 VA minus 310 is equal to 0. Carry across here 310, so you end up with VA is equal to 310 divided by 9, and again I put 34.44, oops, 34.44 volts. So that is what V is, and that is what V Thevenin is, but I have no current flowing through. Alright, and yeah, so you now have what V Thevenin is. So now I have a circuit where I can manipulate my value of my resistance, and I can get what the current will be due to the change. So if I was to use a 5 ohm for some reason, you have IO, which you'll normally see in the diagram with the tutorials. So down here, this is view because this one kind of easy. So with this one, I don't really see. Oh, right. So if this is using Thevenin for this, same analysis techniques. Nothing has changed. They could put a million and one circuits or resistors or whatever. The steps not gonna change at all. It's not. So do not get or be afraid when you see a circuit that looking big. It's the same thing. So they want you to use Thevenin to do this. Same idea, same idea. You open circuit this. Okay, you have to find R Thevenin. So you open circuit all current sources and you short circuit all voltage sources. Okay, then you're looking in from here, trying to get R Thevenin. So you go through, no current flowing through here. And we use our stick man, you walk in, so go through here. Here's our open circuit. Then you go through here, and you come back through here. So in one, nothing flowing here. Nothing flowing here, nothing flowing here. So you basically just have pow, 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 and back to here. So just how they get our terminal. Wow. And the next thing you do, you go back to the original circuit, keeping that there open circuited, because remember that is your first step. And you have to do loop or nodal. I like nodal, use nodal to get what your voltage at this node is and your voltage at this node here. Because remember, that's what Nodal will give you when you find for VA and VB and whatever. So you have VA, VB. And if you want the voltage here now, you will already have it because if VA is here and VB is here, and you want to know the voltage across it, won't it just be VA minus VB? So if there's 10 and there's 5, it could be 5. So just like that, you have your V Thevenin, you have R Thevenin, which would be 1.5 kilo ohm. Okay, you clearly see is 1 plus 0.5. And then you put back in the load that I gave. So by doing this, you just reduce the whole circuit into equivalent resistance and have voltage. This voltage here is basically the voltage that the component will see when you put it in, right? And then now if you want to know the VO here, right? So all you have to do, you have a voltage, you have two resistances, so you can get the current, right? If you want the voltage up across something, it would just be I R. And that's that. That's basically what I wanted to do for this here. Yeah, just the same circuit. It's not really going to change. But for IO will literally just be the your voltage divided by your equivalent resistance. Because basically just want the current through here. It's in series. So the current is the same. And that is it. That is basically the Trinity. So you could use nodal for the V Thevenin. R Thevenin is the same general idea. And you break down your circuit. That is all that is. Nothing more and nothing less. Alright, and that is it. The only hard part in this really is well, unless you're weak in your nodal and you loop, make sure and practice that. Make sure and get strong in it. Can't stress it enough. The only other thing that could trick you up is dependent sources. Alright, so let's try this last one here, which is Norton. I'll call it a night. So with Norton, I'll write it on this side. So Norton is the same steps really, or at least the same initial steps that you can do. So the first step, when you're doing Norton, you're not going to remove your load. You're going to short your load. Yeah, that is the first major change. The second step is certifying our Thevenin, and the steps are the same. You open circuit your current sources, short circuit your voltage sources, looking through here. So with the R Thevenin now, yes, you would just remove here like normal and look in through here. So you have to remove this to the R Thevenin, right? So you're looking through here, you find this could be short circuited. So it'll be 3 plus 6 and 2 in parallel. So that'll be R Thevenin. So 3 plus 6 in parallel with 2. So that'll be 6 multiplied by 2 product divided by the sum. So it'll be that plus 3. And I get 4.5 ohms. Right? So for R Thevenin, yes, you need to open circuit your circuit. Okay, I have a short circuit here. Okay, I want the equivalent in resistance looking in from these points. So that's how to do. Alright? So you have that. So that's the first piece. So remember R Thevenin in parallel for this one. But we don't know what I Norton is as yet, which is your current source. Alright? So now we look back at the first circuit. And remember this is short circuited when you're doing Norton. Remember, when you're doing the R Thevenin, that part is the same what they do Norton or Thevenin. You open circuit, you remove your load resistor. Okay, you want the impedance looking in at that point. So you remove it, you're looking at the two terminals, you get R Thevenin. Now when you're coming back to do the actual Norton, you have to short through the resistor. Alright, and this current through here is I naught. Yeah? So for V Thevenin, will that be the voltage at these two terminals here? That'll be V Thevenin. But for Norton, is iron, where short circuited. So it's the same concept. I have a nice equation that link both of them together. So, but for now, Thevenin, open, voltage between the 2 points. For Norton, you're short, and you want the current through. Right, so there you go. So you want currents. So I could use loop for this one. So I1 and I2. The reason why I choose loop is because just remember when you do IX, if I have IN here, IN would just be I2 because it's literally in the same direction. So that is why I choose it. Alright, so when changing the price of a cheese. If you was to do nodal, you'll have a node here, and this whole thing here will be a node, and you have a resistor. So this here is positive, this minus. So you expect the current to flow this way, which is what I am flowing through. So here you have a voltage, like say VA here, VB. You have your voltage going from a plus to a minus, so you expect it to be positive. So it'll be where you're coming from minus the node after, divided by the resistor in between it, and that'll be iron, as if you were using nodal. So it's the same concept that I showed before. But anyway, we use loop because I want current, and if I find what I2 is, it will be the same as IN because it's literally going in the same direction. So we see in the thought process. So I'll do it up here. So we start here for I1, so it could be 12, and I assume the voltage, a negative voltage drop across the resistors. So it'll be 2I1, and it'll be going through 6 here. It will be minus 6I1 plus 6I2, and you back to where it starts, you make it equal to 0. And then for the other one, you go here, so it'll be minus 3I2, go through here, come through, then it'll be minus 6I2 plus 6I1, and you're back to where it starts, equal to 0. So you can simplify this. So you have minus 8I1 plus 6I2, and I is equal to 0. And this one here, you have minus 9I2 plus 6I1 is equal to 0. So let's go and rearrange this. Just put the I1 first, because as you can see, we're looking at a simultaneous equation here. Yeah, so let's swap it. Nothing major that I do. So there's 1 and there's 2. So you can report a calculator now. So menu, go down to the equation. I think I showed you this last class, simultaneous. You have two unknowns, so you pick 2, you plug it in. So minus 8, 6, 0, well, that's not. Up here, so it's about 12, so this should be minus 12 here. This minus 12, this 12 here will go across to be minus 12. Alright, so just be careful with your reduction. That's 12 here. Alright, I don't think this one here had any numbers, so we good with that. So nice. So I go through. So 6 minus 12. Then you have 6 minus 9 and 0. So you end up with I1 being minus 3 and I2 being minus 2. Right? So I2 in the same direction as IN. So that is okay. So remember, the minus just means that it was actually just going in the opposite direction, which is okay. We're not going to change anything. So you have IN now, which is minus 2 amps. So now you have your circuit IN R Thevenin, and you can now add in resistors in between here, and you can get what the current or the voltage change will be. So in this case, I'll give you the current. So this will be your I, right? And that's it. That basically Thevenin and Norton in a nutshell. Alright, so I'm gonna pause the recording.